Hello. Yes, as you hear, we'll be talking about DiSE, and this is joint work that I did while at Visa Research, and we're hiring and have intern positions. So we asked the question of how would you want to encrypt sensitive data or store sensitive data? And as any good computer scientist does, they first go to Stack Overflow and find a reasonable answer and follow that. And if you do that, you'll end up with something similar to this. First, you'll have your message on some computer. You'll sample a secret key. You'll then run some encryption algorithm. But since you don't want to store your encryption key next to the data, you should probably put the secret key on a different machine, somewhere that's safe. And this is what you end up with. The problem with this solution is that the secret or the server with the secret key could be compromised by some sort of adversary, and then you lose all your security. And this, in general, just sort of forms a single point of failure. And so some of the traditional solutions might be to use trusted hardware, such as an HSM. And this can protect the key, but it has several downsides, including they can be very expensive. There's side channel attacks that if you get physical access to it, and also there's a lack of flexibility in that you can't, the functionality that these HSMs provide are limited. And so what we'd like to ask is there a software-only solution? And an immediate idea that can come to mind is, what if we secret share this key between several servers? And in this case, so long as there's at least one good server or on a server, the secret key remains safe. However, when we want to use the secret key, we're going to have to reconstruct it. So say we want to decrypt the ciphertext C. Well, that means all these servers are going to have to send their share of the secret key to one central location to perform the decryption. And now, again, we have a single point of failure if this location is compromised by the adversary. And so in this talk, we're going to try to tackle this problem. And this is not a new problem. Dating back quite a ways that people have studied it, and this is sort of known as threshold cryptography. And the primary focus of these traditional works have been focused on the public key setting or encryption signatures. Some of the problems with when we started looking at these solutions is that the security that they actually deliver isn't what we're interested in, and their efficiency leaves room for improvement, especially for traditional symmetric key settings and applications. So some of the applications that we're interested in is the encryption of data, possibly a large amount of data, or such as like a password file or tokens while it's just sitting at rest on a server. We're also interested in network authentication and ticketing granting services, such as when you log into some sort of online service. And another application that has come up is when you have a group of devices that are often near each other, such as a cell phone and a watch, and they'd like to help authenticate each other to do a purchase or some sort of other tasks where location and proximity is important. A second general purpose solution is known as multi-party computation. Here, these techniques can compute any function. So in our case, we're interested in encryption and decryption. And there's been several recent works that have sort of targeted this scenario. But some of the downsides is that it achieves even higher overhead in terms of communication and computation as compared to traditional threshold cryptography approaches. And so in our solution, we define new game-based definitions for what it means for symmetric encryption in the distributed setting. And so this entails that we want to be able to perform encryption and decryption operations so long as T out of the N possible parties are available online. We want to ensure correctness. We care about privacy of the messages being encrypted, even from the other servers. And authenticity in that you can't forge ciphertext, and we'll go into more detail. And then we provide a generic construction based upon any distributed PRF. And there's two that we consider. One, which gives us this notion of strong security that we define. And this is based on an exponentiation protocol and zero-knowledge proofs. And then there's a sort of a relaxed notion of security that we consider it's still quite strong, but and this is based on purely based on AES, so it's highly efficient. No public key operations would be required for this scenario. And for example, we can process up to 1 million encryptions per second with while communicating with T out of the end servers. And the latency is also very less than a millisecond. And that's pretty much just network latency. So our setting is that we want to we have n servers total, and we want to just be able to talk to T of them. And with this, generate our encryption or decryption. And we consider the best possible corruption model in that T minus one of the servers that are involved in the protocol can be corrupt. And we still want to be secure against this scenario. We're in the static corruption model where the adversary gets to pick which servers that are going to be corrupt at the beginning of the protocol. And we also assume authenticated point-to-point channels, which will be used later. So with this, I'll move on to our definitions of what it actually means for distributed symmetric key encryption. And so we define it using 3 algorithms. There's a setup algorithm, which is a randomized algorithm that generates a secret key that will be distributed between the parties. So here I use this bracket notation to define a secret sharing where each one of the parties holds their individual share of that secret key. And together they can come together and reconstruct it. Then there's an encryption algorithm, which takes some subset of the secret keys and a message provided by one of the parties and generates a ciphertext C. And so, yeah, here's like a possible subset of all the servers. So this top server doesn't need to be contacted at all. And for efficiency reasons, we only consider the sort of challenge and response scenario. So you get to send one message and receive one message from each server, and they don't communicate with each other. Our definitions don't require this, but this is sort of what our implementation ends up looking like. And only the person initiating the message or the protocol should learn the ciphertext C. And then encryption can be performed, or decryption, excuse me, also takes a possible different subset of the servers and a ciphertext and delivers the message to whoever initiated it. So this being able to work with different subsets of the parties, we call this a consistency property. And then we consider 2 versions of correctness. The basic version of correctness says that if something bad happens to the ciphertext during the protocol or in between encryption and decryption, then when the decryption protocol is run, we either get back the original correct message or it aborts. So that what that means is during encryption, it's possible for the malicious parties to sort of corrupt the ciphertext in some way, but in no way they cannot make the message to decrypt to something else. Then we consider strong correctness, and this here we put extra requirements on this encryption algorithm in that it either generates a perfectly valid ciphertext C or it aborts. So the malicious parties cannot make the protocol do anything other than abort. And this is true during encryption and decryption. And then somewhat unique to our protocols versus traditional threshold cryptography is that we are concerned with message privacy, and that when you run an encryption or decryption, the servers that are helping should not learn the message or the ciphertext that is being operated on. And then we also consider an authenticity property that turns out to be somewhat subtle to actually define, which I'll talk about now. So intuitively, authenticity says that an adversary can't generate ciphertext without using the secret key. In this case, what that means is that it needs to be online and interacting with a T out of the n possible parties. And if we compare this to traditional sort of the non-distributed setting of authenticity, is that the game-based definitions typically go like this, that you allow the adversary to adaptively pick several messages and query this encryption oracle, which gives back the corresponding ciphertext. And then at the end of this, once they're satisfied with the queries, their task is to generate a new ciphertext C prime, which isn't the same as the ones that the encryption oracle gave them, but decrypts correctly. And so if we have authenticity, then this game doesn't succeed with any noticeable probability. So this is a sort of clean definition, but in our distributed setting, there's a lot of stuff going on. There's a protocol going here. There's messages that are being sent and received. And so it's not clear how you can directly translate that definition. But one thing that we can sort of bring over is that when the adversary initiates a encryption, the ciphertext that they learn at the end shouldn't count as a forgery because this is sort of legitimate activity. And so we need some way to say that the ciphertext that the adversaries legitimately generates aren't forgeries. So one idea might be is that you can put these ciphertexts that they generate on sort of like a list, such as in the traditional setting, and then these simply don't count towards forgeries. However, in the case of protocols, this actually becomes very difficult in that this ciphertext might not be well defined if like the adversary simply sends garbage. And so what you need is some sort of like an extractor in these protocols, which would be quite can be heavyweight to implement. In addition, which is unique to our setting versus the traditional setting, is that an honest party can initiate an encryption. And when this happens, we want to say that the adversary shouldn't learn this ciphertext. And if they did, they could output it as a forgery. So this adds additional complications to trying to define what is and what isn't a forgery. And there's also other scenarios that I'm not going to get into that further complicate it. But we sort of take a step back and look at it more sort of abstractly, is that we're in a threshold setting. And so what that means is that the adversary has to at least contact one honest party for each encryption or decryption operation. And so we simply count how many times the adversary contacts an honest party, and then we say that they should not be able to generate more than that many ciphertexts. So there are one more definition of authenticity. And so this allows us sort of to bypass all these complicated edge cases. And so now moving on to my construction, how do we actually implement this? Well, our main ingredient is a distributed PRF. And this has two algorithms: a setup algorithm, which outputs secret keys, shares to each of the parties. And then there's a DPRF protocol, which takes a subset of the keys and an X and outputs the output Y. And this X is public, while this Y value is private to the person who initiates it. And there's a pseudo-randomness property on this Y in that without actually running the protocol, this Y value is sort of unpredictable. And then in the malicious setting, we consider two different flavors, strong. And here's where the Y that is learned from interacting with the protocol is pseudo-random and correct with respect to like honest parties. But in the malicious setting, these corrupt servers could try to alter this the output distribution, and we say, so if we have a strong pseudo-random distributed PRF, then this can't happen. It's always correct or abort. And then we consider a weak notion, and this only requires pseudo-randomness, where the adversary can influence the output of this Y. But and we'll build two different types of schemes based on this, which both achieve strong correctness, but but different efficiency. Just to give you an example of what these look like. So one of the approaches based on a DDH type assumption is to perform Shamir secret sharing in the exponent of these. And so these lambda terms can be computed locally. They're just sort of public based on Shamir secret sharing, and then they can multiply it with their local key. And then each of these individual terms can be one of the Ys that gets sent back to the initiating party and reconstruct the final OPRF value, or DPRF, excuse me. Too many things. So as a warm-up, here's sort of like where we started when we started thinking about this. How could you implement such a protocol? And the traditional approach for authenticated encryption is this sort of encrypt then MAC paradigm. And so this is sort of what we'll do here. First, we'll sample a nonce R, then apply the DPRF to this value R and get back a secret key Y. Use this to encrypt the message. And then to get authenticity, we need to MAC this encryption E. And to do it, we'll simply use the DPRF again and get our MAC T, and then our ciphertext will just be the concatenation of these terms. And one issue with this is that it's 4 rounds, and we were really interested in getting good efficiency of just having 2 rounds, which also enables a variety of other nice properties. And it seems like this deriving this key Y has to be distributed to prevent local decryption, and that you need to contact the other parties to be able to decrypt later on. And this MACing term seems to have to be distributed to ensure that once you generate one of these ciphertexts, you can't change it out later by manipulating what the ciphertext is. And the traditional encrypt and MAC approach has been shown to be insecure, and so we had to come up with some other approach to get around this issue. And our idea is that we can somehow, in the first round, bind the message M to the key that we generate in the first round. And what this looks like is that we still generate this nonce R, but we use it as the randomness to a commitment and to get Q of the message. And then we apply the DPRF to this Q message and get back our key Y. And then we run an encryption, and we have to encrypt the randomness now in order to check the commitment later. And our ciphertext is this commitment Q, which is sort of now is acting like a MAC, and our ciphertext E. And then decryption is sort of just the obvious thing. You query the DPRF again on Q, and you can then decrypt and check the commitment. Intuitively, what we want to say is that this commitment is sort of binding the ciphertext to the underlying message M. But there's some subtleties here, in that here's one possible attack is that you can use, you can keep Q the same, which has the sort of this distributed property applied to it, but you can change the underlying ciphertext E. So you might keep the same message, it still decrypts to the same message, but you can generate additional ciphertext. So we would lose authenticity. And so to get around this, we ensure that this encryption scheme is deterministic. And this is not too hard to do, but it takes extra care. And then there's also another subtle attack here, in that an adversary can masquerade a decryption query as an encryption query. Since the decryption and encryption from the protocol view looks very same, you just send a commitment and you get back the corresponding value. And so an adversary could come along and say, hey, let me encrypt this message which has this commitment Q, but you're really decrypting one of the ciphertexts that you've observed from somehow. And so we want to prevent this, otherwise message privacy wouldn't be ensured. And so what we can do is add this sort of identity tag here, which says that when you're performing an encryption, you can only query the DPRF using your own identity, and that way you can't masquerade decryption queries as encryption. And so this is our full protocol, and it's quite simple. We just run the DPRF and correctly construct this ciphertext. And then we provide several different instantiations of this DPRF. One has the sort of strong notion of correctness and privacy and authenticity property, while the weaker notion only doesn't get our strong notion of correctness, in that where bad ciphertext would be caught, encryption or decryption. And we provide several implementations. So for performance, here we consider 18 servers and a variety of thresholds. So here at the top, our threshold t equals 2. That means that you have to contact 2 servers, maybe one is counting yourself, to generate a ciphertext. And you can see that we can perform up to 1 million encryptions per second, where the DPRF is based on this just any PRF. In this case, we use hardware accelerated AES. And so it's very efficient. And then these DDH-based protocols don't get as high of throughput because they require exponentiation. But the last one here with 226 encryptions per second also gets a strong notion of correctness, where bad ciphertexts are caught immediately, encryption. And then we can also consider latency. And here you can see with a threshold of 2, our latency is 0.1 milliseconds. So it's very efficient. And even with a very high threshold of 16 parties, our latency is only 2 milliseconds or up to 55 milliseconds with a strong correctness property. And we also consider various other values of n, so number of parties, and we achieve roughly, with smaller n, you get more performance, but it's not too much different than this. And so in summary, we initiate the study of threshold symmetric key authenticated encryption. We propose a general framework that can be implemented with any distributed PRF, and we implement it using a variety of them. Our implementation is very fast and can scale to a large number of parties. Some future directions is that there's so I was talking about the masquerading encryption as a decryption. The inverse is also true, but maybe it's not as bad. So you could look at trying to prevent such attacks. And then you can also look at other forms of security, such as protecting against nonce misuse and in the many user settings. So these are just sort of different environments to analyze the security of the protocol in. And with that, I'd like to thank you, and let's DiSE.
Thank you. Questions?
I have probably a stupid question, but could you shed some light on why an authenticated encryption mode doesn't compose with the DPRF?
Oh, yes. So one of the main problems is just using a traditional authenticated encryption scheme is that you might be able to generate many ciphertexts. So in traditional setting, the person who's generating the ciphertext will do it honestly, but here the person generating the ciphertext could be an adversary, and so they could generate many ciphertexts based upon. There might not just be one way to generate that ciphertext. They could keep generating many ciphertexts after they derive the first initial key, and so you lose authenticity because an adversary knows more information than in the traditional setting where an encryption oracle performs the encryption.
So it's a little. I have just a little bit of like an ill-formed question, but
It's okay.
I'm just curious, like order of magnitude. If you would compare what you're doing to what you could get with like a good secure computation protocol pre-processing the OTs. I mean, can you give an order of magnitude how much faster you would be?
So if you pre-process the OTs,
And then use OT extension, right?
oh yeah, sure. Without counting that, yeah, it would seem we're 2 orders of magnitude more efficient. So like the actual communication that we send is like, at least in the AES based case, we send 128 bits to each party and then we get 128 bits back. So like you're going to be much more than that, order of magnitude more.
Are you assuming a wide area network there, or even over? I mean, I know the communication doesn't matter, but is it you're saying it's communication dominated rather than computation?
Well, I don't know in this case. It's hard to say. For short messages, it's probably communication bound, and yeah, and in that case, like if you use OT based approaches, you're going to be communicating, more, even if the round complexity isn't much different.
I mean, it depends on N and T also, but
yeah. But
like let's say even 2-party, you think you're 100 times faster?
I would think so. Yeah, at least between that and 10.
Questions? Maybe I would have a short one. Maybe I didn't miss something there. On your experience slides, for like the threshold of 16.
Yeah.
Why is number going up?
Oh, because so they only go up in the AES based approach, and this has to do with in this AES based DPRF. It has this replicated secret sharing scheme, and what that means is you have to you send the share to more than one person, and you actually get some sort of bad combinatorics right when the threshold is at 1/2. And so when you start getting back to where you need almost all the parties, you don't have to account for so many different possible subsets. That gets you better performance.
All right, thanks. Thanks for the game.